Okay, let's get started. Decidability. So, decidable properties and computable functions. Definition of a decision problem. A decision problem is said to be decidable when there's some program where, when it's given an argument, it says whether the answer is yes or no. Yeah, this is all being recorded. But what is a program? A program in what language? Let's say we have a decision problem concerning words in some language sigma star. So the set of all possible words, including the empty word, where a word is a list of characters from our alphabet sigma. This can be expressed in two ways. So we can either express a decision problem as a function of mappings of words to yes or no. So we might have something like AB goes to yes, B goes to no, A goes to yes. So we could have a function which is defined as a mapping like this. Or we could say it's a subset of sigma star. So the set of good words. So we might have A, AB, AAB. And these are the accepted words in some decision problem, which result to true or yes. So that's two ways we can represent a decision problem. And now we want to think about whether that's decidable or not. So let's first think about solving a problem on a Turing machine. The tape alphabet is sigma or space, so we can also just have a blank character. And the set of return values is yes or no. We start execution with a word W on an otherwise blank tape, so we have a bunch of spaces, we have a word, and we have more spaces. And the head is on the left of the word, on the cell to the left of the word in this case. Okay, so they've done this. At the end of the execution, the head is where it began, the tape is blank, and the machine returns yes if W is a good word, and no if it's a bad word. If there's such a Turing machine that does this and tells you whether a word is good or bad, then we say this is decidable. But if there's not, then it's undecidable. We can also think about two-tape Turing machines, two-dimensional Turing machines, all these different types of Turing machines, because we might see Turing machines as something that's restrictive when we're making an algorithm. But the idea is, if we can solve it on a fancy Turing machine or a two-tape Turing machine, we can convert it to a Turing machine anyway. So even if we can then say we can algorithmically solve it on something like a two-tape or a fancy or a 2D Turing machine, then we can also say that implies we can solve it on a normal Turing machine, and so it's decidable. Many different notions of algorithm have been proposed that appear to be more expressive than a Turing machine, but as far as decision problems on words are concerned, a fancy notion is no more expressive than a normal Turing machine. So that's kind of that just put into words. And so it means this notion of decidability is robust. All these different definitions are basically the same thing. If we can code it in Java or a Turing complete language, or we can do it on a 20-dimensional Turing machine, then we can do it on a normal Turing machine, and then it's decidable. Perhaps somebody in the future will invent it. Okay. And then we have something called Church's thesis. We need to be familiar with. So Church's thesis states any decision problem on words that can be solved by an algorithm can be solved by a Turing machine. So if we have anything we can solve algorithmically that results in yes or no, then we can solve it with a Turing machine. But we need to have that robust algorithm which solves it. Another version is for functions. In this case, the Turing machine would start with a word, and it would stop with the word f of w on that blank. So we might not just think about decision problems, we might also think about functions which map a word to another word. So we can either have sigma star going to either yes or no, or we can have sigma star mapping to another sigma star. So this would be a decision problem, and this would be a function. And these can all either be decidable or undecidable. Okay. Decidable problem TM exists, undecidable problem no TM exists. Undecidable semantic property, two programs with same output, but one doesn't have the property. Decidable semantic property is just when they all have the same output. So if we had a property like that's always true or always false, then it's a decidable semantic property. But if it's not always true or not always false, then it's undecidable, based on Kleen's theorem. Rice's theorem, not Kleen's. Rice's theorem. No worries. Okay, so we can encode anything as a word. Natural numbers, integers, arrays, anything we can store in a computer essentially. is binary, so we can even encode that as a word, just as binary. And we may talk about undecidable problems, undecidable properties, subsets, languages, but the idea is we're encoding this into something we can then run on a Turing machine. So that's what we're talking about when we're saying undecidable. So in the exam, how would we say something's decidable? If we can think of a Turing machine that solves it, then it's decidable. If it's a semantic property, which quite often it will be with the exam questions, if it's a semantic property that's not always true, and it's not always false, then it's non-trivial. And then by Rice's theorem, we can say that that semantic property is undecidable. Okay. Primitive and basic Java. So, let's give the name of primitive Java to a Java-like language with only the type nat for unlimited natural numbers. It has the following facilities. So you can create variables, increment a variable, decrement a variable, conditionals like if something's true then run m, else n, and repetition of some code a fixed number of times. Just to get started, they've given us some encodings, so we can encode nat j equals I as setting j to 0 and then increasing j I times. So we can use these to sort of derive all of these different things we can do. Okay, computing functions. Consider a program that's k-ary, so it has k inputs. If the program's in primitive Java, every list of inputs, x in the natural numbers to the power of k, it will terminate with an output. And so the program computes a total function from nk to n. Reason it's total is because it's defined for all values in that domain. If the program uses while loops, there's a possibility of it not actually terminating. And so the program computes to a partial function. For example, this unary program will return 2 if the input 0 or 1, but otherwise it will hang. So it will increase j to 2, and then while j is more than 0, so while 2 is more than 0, if input 0 is less than or equal to 2, then we decrease. And so this program will only compute a partial function that sends 0 and 1 to 2, but it's undefined for all numbers that are greater than or equal to 2. Another example they gave us is the Ackermann function, and the idea is this function is so a primitive recursive function includes all the familiar functions such as comparison, multiplication, exponentiation, factorial, and so on. They also include all functions that can be computed in a Turing machine in polynomial time, exponential time, and much more. People used to think that they were only functions on natural numbers that could be computed algorithmically. However, in 1928, Wilhelm Ackermann made a shock discovery, a function that can be computed algorithmically but is not primitive recursive. So the Ackermann function, actually a simplified version, takes 2 arguments and it's given as follows. So if we pass in 0 and some number n, we just return n plus 1. If we pass in n plus 1 and 0, we then call it with m1. And then if we pass in n plus 1, so 2 natural numbers, none of which are 0, then we call the Ackermann function with those 2 arguments, m, and then the Ackermann result of m plus 1 n. So Ackermann is saying you can have total and Turing complete programs. I believe so. So, I mean, yeah, this was the first function that can be computed algorithmically. That isn't primitive recursive. That isn't just some function on natural numbers. So I guess that is why it's quite significant. And so we went through a proof by induction that it terminates. For mn in natural numbers, let qmn be the statement that the evaluation of the Ackermann function mn terminates. We'll prove that for all values of m and n in the natural numbers, q of mn, the base case, for all n in natural numbers, q of 0n terminates because 0 anything just returns n plus 1. So we know that this terminates. Q of 0n terminates. For the inductive step, we suppose that for all n in natural numbers, q of mn terminates. So a of mn terminates, which is represented by this q of mn statement. And we want to prove that for all n in natural numbers, it also terminates for m plus 1 n, assuming it terminates for mn. So we can do this by induction. The base case says that q of m plus 1, 0 holds because am1 returns a value p, by the outer inductive hypothesis. So, okay, so this is the one where we did with nested induction. Okay, so this is our first assumption we've got. And so, our base case, we're going to use this. We're using this as our base case. And this holds because this returns some value p. And m is less than m plus 1. So we can assume that this is going to terminate. And so this will also terminate because we're just calling it with a smaller value. For the inductive step, we want to prove that m plus 1n, or supposing that m plus 1n terminates, we want to prove that q of m plus 1, n plus 1 terminates. So we want to prove that this n implies this m plus 1 also leads to it terminating. A m plus 1n returns an answer p by the inner inductive hypothesis. So I believe that's based on this assumption. M plus 1p and a mp returns a value q by the outer inductive hypothesis, i.e. q mn, and so a m plus 1 n plus 1 also returns q. Because we're calling this with... Okay, so they've kind of done a nested induction here. Does anyone think they can explain this better than me? Because I think I'm a bit lost. The Ackermann function cannot be written in primitive Java, however it can be written in basic Java. Okay, this is just... I highly doubt this is gonna like come up as a question, or if it is, I don't think... I think this is just a bit of an evil proof, really. We don't have to specifically know this function. Yeah, no, we don't. But I feel like this nested induction they're doing, we kind of might want to know, but it's just a bit evil. Because we're using an outer hypothesis, and then we're also using an inner hypothesis, and we're using both of them for the inductive step of the inner induction. But yeah. Okay, shall we move on? We can always come back to this after. I just want to get through decidability. Okay. Examples of decidable and undecidable properties. So here's some examples of problems and their decidability status. Saying whether two regular expressions are equivalent. This is decidable because we've got our algorithmic way of doing this. We can trace through both of them at the same time, see if all of the corresponding states are both accepting or both rejecting. So this is decidable. Problem of saying whether a CFG accepts a given word is also decidable because we can systematically compute, we can systematically derive something from a grammar by replacing occurrences of variables. The problem of saying whether a CFG accepts any word at all is also decidable because that's just essentially trying out some sort of word. Yeah, to see if it accepts any word at all, we can just derive it from our start variable into terminal characters, terminal symbols. The problem of saying whether a CFG accepts every word is undecidable because we can't exactly test it for every word in the alphabet because the word can be infinitely long, and so we can't actually we can't create a Turing machine which does that for every possible length. The problem of saying whether a given context-free grammar is ambiguous is undecidable. We can't say whether a CFG is ambiguous with a Turing machine. There's some more examples here of undecidable and decidable problems. Yeah, okay. So there's many examples, we'll see some of them, but the reason we want to understand this notion of decidability is because we might be given some sort of problem or some sort of property, and we want to say whether it's decidable or undecidable. One term we also need to be familiar with is semi-decidable. So a property P of natural numbers is semi-decidable when there's a program that when it's executed on some number n, it returns true if n satisfies P and runs forever otherwise. For decidability, the program would have to return false otherwise. But with semi-decidability, it just returns true if it's in the if it's accepted or if the property is true, and it just doesn't return anything. It just hangs if the property is not accepted. So an example, saying whether a given integer coefficient polynomial in P in several variables has an integer solution. This is semi-decidable because we can treat lists of integers as natural numbers. We can just loop up. We can just loop through all of our integers, and as soon as we find an integer where it solves that polynomial by just substituting it in. So say we had something like x squared plus 7x plus 12. Okay, so I mean this has an integer solution. We can try it with 0. Doesn't work. We can try it with 1. Doesn't work. We can try it with x squared plus 7x. That is not a good example. Okay. I believe that should work. Okay, we can try this with 1. It won't work. We can try it with 2. It won't work. We can try it with 3. When we sub 3 in, we get 3 squared minus 7 times 3 plus 12. And this, in fact, is equal to 0. So we've tried it, we've reached the solution, and then we can return true. So seeing if an integer satisfies this. Whereas if we have another polynomial, maybe something like this, I don't believe there is any integer x which satisfies this. This is going to be some real number, some decimal, or maybe some complex. But we'd try every integer up to infinity. We'd never stop. We'd just keep looping up and try every integer. And so this would just hang. It wouldn't actually return false, but it would only return true if there is some integer eventually. And so this is an example of a semi-decidable problem, seeing if an integer satisfies this equation. Do we only have to know how to prove semantic properties are undecidable? I believe so, but I think the definition of decidability and undecidability we want to know in general, because that could apply to syntactic as well. Syntactic properties. Problem which is semi-decidable can be undecidable, right? Problem which is semi-decidable can be undecidable. So a problem's undecidable if there is no Turing machine that decides it. I believe so, yes. So yeah, I think so. So with semi-decidability, any property that's decidable is also semi-decidable, just because we can just create a while true loop or something in the event that it returns false, or when it would return false. And if both P and the negation of that property P is semi-decidable, then P is decidable, because we can merge those two semi-decidable machines or algorithms into one, and just return true when the first one returned true, and return false when the second one returned true. Yeah. P could be semi-decidable, but not P could be undecidable. Yeah, so, yeah, exactly. So, in that case, it can be semi-decidable and undecidable. Okay. That's everything about decidability. Are there any questions about that? But yeah, that's everything on semi-decidable properties and decidability in general.